Ever wonder how your phone's spam filter knows exactly which emails to block? Or how doctors use test results to make life-saving decisions? Behind the scenes, there's a whole world of math helping computers make sense of messy, real-world data. Today, we're diving into a study that's changing how we understand one of the tools these systems use: Bayesian algorithms. Let's start with a simple question. How do you predict something that's either yes or no, like whether a customer will buy a product or if a patient has a disease? That's where Probit regression comes in. It's like a bridge between raw data and a clear answer, turning complicated numbers into a 0 or 1. But here's the twist. When you're dealing with massive datasets, think millions of variables and observations, traditional methods can get stuck in a loop. That's where Bayesian methods step in. Instead of just crunching numbers, they let you build in what you already know, like a detective using clues to narrow down suspects. But even then, there's a challenge. Sampling from complex probability distributions is like trying to find a single grain of sand in a desert. That's where Gibbs samplers come to the rescue. Imagine you're solving a puzzle, but each piece only fits if you adjust a few other pieces at a time. Gibbs samplers do something similar. They break down the problem into smaller, easier steps, gradually refining their guess until they get it right. But here's the big question: how fast can they do this? That's what this study is all about. The researchers focused on two popular Gibbs sampler strategies: data augmentation (DA) and collapsed Gibbs (CG). Think of DA as a brute force approach, iteratively refining guesses until they stabilize. CG, on the other hand, is like a smarter shortcut, collapsing some variables to speed things up. But how do they stack up in the real world? The answer lies in something called Kullback-Leibler divergence, a fancy way of measuring how different two probability distributions are. The study shows that the mixing time, how long it takes the sampler to stabilize, depends on two things: the structure of your data and the prior you choose, your initial assumptions. If the data is well-behaved and the prior is chosen wisely, the samplers can stay efficient. But if things get messy, they might get stuck in a loop. Here's why this matters. If you're working with high-dimensional data, like genetic sequences or social media trends, this research helps you pick better priors and know when to trust your model's results. It's like having a roadmap for navigating a labyrinth, ensuring you don't waste computational resources on dead ends. Now let's break down how these samplers actually work. Imagine tracking a moving target with only intermittent snapshots. The algorithm compares values over time, using a threshold called epsilon to decide when to switch strategies. If the difference between measurements is large, it adopts a more aggressive sampling method. If it's small, it switches to a more efficient one. This adaptive approach ensures it doesn't waste steps on unnecessary calculations. The key innovation here is how the study quantifies stability. When the algorithm detects that a value has stabilized, meaning its fluctuations fall below epsilon, it stops iterating and reports the result. This avoids the pitfalls of infinite loops while maintaining accuracy. The math behind this involves Markov chain convergence properties, but the core idea is simple: adapt, observe, and optimize. This research isn't just theoretical, it's a practical guide for anyone working with complex models. Whether you're training AI, analyzing genomic data, or building recommendation systems, understanding these samplers' behavior can save you time and computational power. Thanks for watching. If you'd like to dive deeper into how algorithms tackle complexity, hit subscribe and let me know in the comments what topics you're curious about. Stay curious.